particle now has spread out over time, right? And that's a phenomenon called dispersion. And that's what we're going to be talking about today in a little bit more detail.
Do we have to keep that continuously measurement?
Oh, yeah, so that's very interesting. If you look in the back of Griffiths, right, it's related to this thing called the quantum Zeno's paradox, right? And it's the idea that you have to continually keep looking at something to know where it is. And so the paradox comes in about a boiling pot of water. Like if you always are looking at like a boiling pot of water, it might not ever boil because you would always keep it in this particular state. Right? So I encourage you to read that part. It's in chapter, it's right at the end of your book. I forget what chapter it is, but it's called the Quantum Zeno's Paradox.
Right, so particles are like children. You stop looking at them, they disappear.
That's very good. They disperse. All right, so this is called a dispersion relationship, and that's really what we're going to be talking about.
Chapter 12, right after the short discussion.
Yeah, I thought it's all in that whole thing on quantum mechanics, like what does quantum mechanics mean, what are the funky implications.
There was a spooky section of this that
Yeah.
talked about the quality.
So it's very nice stuff. So this is called dispersion. And so we're going to be looking at essentially the dispersion of the wave packet. All right? Further, if you plotted this wave packet, if you plot it again in green, and this is x, all right? But when we're looking at x, what this wave packet kind of looks like. So notice this is the wave squared. This is going to be sine general of x and t, but not squared. Sorry, not squared. Just the wave function itself. And then this is figure 211. All right. That if you took this thing and you tried to say, what does this thing look like? So this is sine general. This is figure 211. Maybe it's better to do this. Directly connect this expansion that we just did to this picture. All right? And now what you see is the following, is that this stuff, right, is essentially the envelope. Right? It's shaping the envelope. And what is the stuff inside of here? Well, so, the perfect draws it like that. But that would be like 1. And then we would need another one, of a different. So these are different wavelengths.
That's
right?
the basis set.
That's the basis set. All right, so then this one might be faster. All right, these things are the basis set. These are essentially the plane waves. And these are the plane waves that are going into making your wave packet. So what I'll do is I'll call this a wave packet. The answer I'll call a wave packet. And the wave packet is made out of the envelope. All right? And inside of the envelope, the thing that's going into making the envelope are the basis sets. Yep, plane waves.
Does it not go to 0 at minus infinity plus infinity because it's not normalizable?
So here's the scoop, and this is the wild thing that you only get in experience. What do you think happens to this wave packet at infinity? So the envelope. What do you think the envelope looks like at plus or minus infinity?
0.
It goes to 0. And the reason is the whole envelope is what represents the particle, and so that has to be normalizable. And so therefore, the envelope is going to go to 0. Okay, but do these things go to 0?
Plane waves are not
Individually.
normalizable, no.
What's that?
Plane waves are not normalizable.
Okay, plane waves don't go to 0, But what about the sum of the plane waves on this side and the
Somebody zero.
It's the sum of the plane waves. So here's the wild thing, is that what we just did with a Fourier integral is we found out a combination of the plane waves, right? They're going to add up to 0 inside of here, right? And it's part of the weighting. You know, as k goes to infinity, what happens to this thing?
It gets smaller.
Yeah, maybe it's not the sum of the plane waves that individually go to 0, but certainly the envelope goes to 0.
Because 1 or -1 over infinity is 0.
Yeah, it goes to 0. So in essence, this thing, this part, the envelope, kind of weights it and makes it normalizable. All right? So here's what we're going to find next. All right? So did that answer your question, Matt?
Yeah,
Do you kind of get it?
yeah.
So the wave packet
Yes.
definitely goes to 0, and I guess it's mainly because of the weighting of the envelope. You need this probability density, by definition, to go to 0 at plus or minus infinity.
And what causes it to go to 0?
Yeah, so it works.
0.
Yeah. All right, so the thing that we come to recognize as our free particle is really not the individual plane waves, right? It's really this wave packet that represents our particle. All right, now, let's try to resolve another issue before we get to dispersion. All right, what did we say? These plane waves are our stationary states, right? And they're not normalizable. Well, we just kind of took care of that, right, with the envelope. All right, but now we also have that the velocities have the classical. So does that bother you as much right now?
Not yet.
Okay. Why? Because is our particle represented by these individual waves individually?
No.
No. So even though these might not go to classical speed, what do you want to go to classical speed?
The whole package.
Okay, that's it. Okay, so here's what you do, is the velocity of the bases, you know, my plane wave bases, equals half of V classical. And by the way, these are called phase velocity. These are the phase velocities. And those phase velocities definitely go at half the wave of the particle. But what I'm going to call my wave packet now is the velocity of my wave packet. What do you guys want it to be?
Classical one.
You want that to be the velocity of your classical particle. And that's called V as a group. And that's called the group velocity. And what we will show is that the velocity of the group will indeed equal V classical.
So which one is equal to half of classical velocity?
Okay, so can anybody tell?
Any of the individual waves will have half the velocity.
Okay, and any one of the individual waves came as a result of our stationary state solution, right? And why we said we didn't like our stationary state solutions right away, because they had to have the velocity. So I think this is very nicely done. Right? Does everybody kind of agree? That clears up a lot of stuff. Alright, I think that was good. Alright, so this is the thing that represents our particle, and the next thing is to show V group equals V classical. Alright, and for me to do that, I'm going to follow 100% Griffiths. I'm going to add nothing new. I'm going to go step 1, step 2, step 3 in Griffiths. Alright? But to show dispersion, I'm going to use a little bit of Griffiths, and I'm also going to use Harris's book. Okay? The modern book, Harris, yeah. And it's in particular chapter 6, where he does a great job at it. Griffiths actually does get to this, but it's hidden in problem, what did I say for homework? 222?
22.
Yeah, 222, I think is part C. It's kind of hidden in there. Okay, so let's continue. And Again, my goal here is to show V group equals V classical, all right, and then show dispersion. And I'm
In one, we'll go over chapter 6 at all, or we just...
I will show you to the extent that you need it. You know, my assumption is I can't assume that everybody has Harris, right? But if you have Harris, it will really help. Okay?
I was just wondering if in modern we're going to be going over chapter 6 at all.
Oh, for modern?
Yeah.
No.
Some things that we've done here.
It's one of those then.
Yeah.
There's some things we go over here that we're not covering in modern, so we can...
That's why you're getting the best of both.
That's why I figured I'd ask.
Yeah, go ahead.
That arrow on the left of the wave packet,
This one?
yeah, what's that, what is that saying?
Okay, so what does this arrow mean down right here? Why do I have that arrow?
That means that the equation is for the entire wave packet.
That this whole thing equals this whole picture, the whole wave packet picture.
One part of it's the envelope, one part of it's the...
This part?
Yeah, I get all that, and the other part is
Yeah.
the individual waves that
Yeah.
are said.
Yeah.
Classical velocity.
Yeah.
So
Cool.
why is the phase velocity half the classical velocity?
That we're gonna find out in the dispersion relation. I mean, I don't know what the answer is, but the answer is it is half the velocity, and it's not my particle. All right. Why does it come out to be a half? Is that a coincidence? Is that what you mean, or?
Yeah, like in different circumstances, the phase velocity is sometimes bigger than the group velocity, and
Yeah.
in this case, it's just exactly half. It's just
Yeah. So the only answer I can have is that the phase velocity doesn't represent the real thing. But you can still, what we're going to show is that this continuous summation going to the Fourier integral gives us a group velocity that does have the velocity of our particle. And that's what matters. Okay? Okay, so now it gets a little bit dicey.
Tell us
and
why you conduct your rise.
So here's where I'm going to be following. I'm going to be following page 65 in Griffiths. All right? And it will get a little bit dicey, and I'll try to lead you guys through it. All right? So let's go. Well, I guess before I do that, there's always something. To continue with this problem, what we did on Thursday, all right, is we looked at some limiting cases. And we looked at some limiting cases.
what A
All
is
right,
really small.
So going back to this problem right here, another illuminating part of all this is that we can not just look at the x, by the way guys, is this the x space or the k space representation?
Okay, so
This is k-space representation of the wave function, right? This is the x-space representation of the wave function. And this is the x-space representation of the probability density, right? Okay, another illuminating way to look at these things is to look at the difference between the x-space. So again, I'll write it over here, maybe something like this, the x-space.
K-space should just be a P.
This is the x-space of, psi of x, and in particular, this is t equals 0, right? This is x space rep, and this is minus a, and this is plus a. And what we can do is, another way to really get a feel for Fourier transforms and Fourier series is to look at the other space representation. So when we look at the k-space representation, we're going to look over here as a function of k. So this is x space and this is k space. And again, I went over this a little bit on Thursday, but what we did is we looked at a couple limits. All right? And the first limit is to look at, this is just the wave function not squared. This is the wave function, not the probability density. And this is figure 2.9. So figure 2.9. Okay, so what we did is, Griffiths did is he looked at two limits. The first limit, so I'll do it in blue. The first limit, well, let me do it in red, so I can add it right on top. The first limit was to let A approach 0. So when you let A approach 0, minus theta plus theta gets very small, and this becomes very spiky, right? And so what that tells us is that delta x